Hello, everyone. My name is Matheus. I'll be talking about my joint work with Matt Weinberg called Proof of Stake Mining Games with Perfect Randomness, and we are both from Princeton University. So blockchains, they are simply mechanisms where, for example, imagine Alice owns one Bitcoin and she wants to send her Bitcoin to Bob. The way that she could do that is by asking a miner to add her transaction in a block. To do that, a miner has to implement, ideally a miner would implement the longest chain rule that was first proposed in Bitcoin, where the miner extends the blockchain by adding a block with Alice's transaction by solving a crypto puzzle. To incentivize miners to participate, miners receive new coins as a reward. So for example, imagine a miner creates a new block containing Alice's transaction, and that miner is going to receive in the current rate, a miner is going to receive 6.25 Bitcoins for creating this new block. However, as I know, Bitcoin consumes a lot of energy. In January of 2021, was estimated if Bitcoin was a country, it would consume more energy than all but 28 countries in the planet. Despite of all this energy consumption, Bitcoin can only process 7 transactions per second. My talk is focused on a different type of blockchain that overcome the limitation of proof of work. So proof of stake is a promising alternative where instead of requiring miners to solve crypto puzzles to create a new block, we're gonna have a mechanism that is able to sample a uniformly random coin in the system. And the owner of that coin is gonna have the privilege to create the next block. For example, if we sample one of miner 1 coins, the miner 1 can now create a block adding new transactions in the blockchain. But one natural question you might ask is if these proof of stake blockchains preserve the economic incentives that we have for proof of work. One example is that, for example, imagine that instead of a miner extending the longest path, a miner could instead publish his blocks in a different alternative path by removing honest blocks from the longest chain. By doing that, a miner can increase the fraction of coins that they have in the system. And that's particularly concerning for proof of stake, since the probability that a miner is going to create blocks in the future is proportional to the fraction of the coins that they have. To make it more clear, consider the following example where we have an adversary that owns 30% of the coins in the system, where in the lifetime running a simulation, we find a strategy that was proposed by IL and Searer in 2013, known as selfish mining, where in this particular strategy, if a miner owns 40% of the coins, they are able to increase their fraction of the coins in the long time horizon. In a proof of stake blockchain, that implies that an adversary could make the probability they're going to create blocks in the future arbitrarily larger. So our main goal is to understand under which conditions a particular adversary that's trying to maximize the fraction of blocks that they add would not, the honest mining fact would be the ultimate strategy if that's their objective to do. So in particular for selfish mining, we know that as long as adversary owns more than 1/3 of the coins, then selfish mining would be a better strategy than being honest under this utility assumption. So in other words, what we'd like to have is the property that honest mining forms a Nash equilibrium. We're assuming that everyone is following the honest mining strategy. No miner would have incentive to change their strategy to another strategy that would allow them to improve their fraction of the coins. Under this question, unfortunately, we had a negative result by Brown-Cohen, Naranian, Pesamas, and Weinberg, where they gave formal barrier to achieve this goal, where they showed that any longest chain protocol, so a protocol similar to Bitcoin, but where mining is computationally efficient, which is different from proof of work, where mining is inefficient. And if in addition, if all the source of randomness that the protocol uses to sample a coin comes from the blockchain itself, then they show that honest mining would never be a Nash equilibrium. So to overcome this limitation, What we propose in this work is to use an external source of randomness, which is commonly known as a random beacon, which was first proposed by Rabin in '83. So a random beacon is just as a source of randomness that's trusted, and in discrete time steps, this source of randomness reveal random bits to the system and to everyone in the network. Under this assumption, we show that honest mining, in fact, becomes a Nash equilibrium when no miner owns more than 30.8% of the coins. So we go from the point where honest mining would never be a Nash equilibrium to the point where honest mining becomes a Nash equilibrium. And random beacons have received a lot of attention in recent years, especially in the blockchain community, but in other application domains. So before I show how we can obtain our Nash equilibrium guarantees, let me first formalize the model that we're going to be working on. So for my examples, I'm going to be assuming, I'm going to be using thinner arrows to denote blocks that are still hidden, and thicker arrows to denote blocks that are public. So that means that the miner revealed that block. And I'm going to use red blocks to denote blocks created by an adversary, and blue blocks created by everyone else that's not the adversary. So in our game, we're going to assume that the adversary owns strictly less than half of the coins. And that's because if an adversary owns more than half of the coins, then it's not hard to see that honest mining would not be an equilibrium. So the way that the game is going to proceed is that in each time step, we are going to sample one coin. And we can do that because we have access to a random beacon. We can use this external random source to sample a coin uniformly at random. And the owner of that coin is going to receive the privilege to create a block with timestamp T. And in addition, block T, a block of timestamp T, can point to any block that that has a smaller timestamp. For example, if the adversary receives the privilege to create block 5, then block 5 can point to any block that has a smaller timestamp. But in addition to that, we are going to assume that once a block is published, that block cannot be used anymore. And the reason is that whenever an adversary publishes 2 blocks with the same timestamp, then it's clear for everyone in the network that that miner is deviating from the protocol, which means that we can punish that behavior. So we can design a punishment mechanism to disincentivize a miner to publish 2 blocks with the same timestamp. So we're going to assume that once a block is published, that block cannot be published anymore. But as long as that block has not been published, that block can be published to any block that arrived earlier. So before going more details, let me highlight what's the main distinction between proof of work and the proof of stake mining game that we are considering. So the main difference is that in proof of work, the validity of a block depends on its content. So whenever a block is created, that block contains the hash to the ancestor block in the blockchain. But once that block was created, we cannot change the content of the block without breaking the hash of block 5. So that means that once a block is created, the ancestor of that block was chosen even before the block was created. But that's different from proof of stake, where the validity of a block is coming from this random beacon that's giving our random source. And that our block can point to anything that arrived earlier. Now let me give you a high-level idea of how we can prove a Nash equilibrium guarantee in this setting. And surprisingly, the proof boils down to analyzing 3 main cases. So the first case is going to be the following one, where the adversary, the honest miner creates the first block. Recall, if the adversary is following the honest strategy, then he must extend the longest path, which is the path that contains block 1. But an adversary could potentially remove block 1 from the longest path. However, our first claim is that there is in fact an optimal strategy that would never fork block 1 from the longest path. To prove this, I'm going to introduce, I'm going to show an even stronger result. So to prove that particular result, we show that there is an increasing sequence of blocks in the longest path that an adversary would never remove or never have incentive to remove from the longest path that we call checkpoints. So to define this sequence, we define the first element on the sequence should be the block 0. Next, we recursively define the next checkpoint given the prior one. So the checkpoint P1 is going to be the first block after P0, where the number of blocks that the adversary owns in the longest path from P0 to P1 is at least the number of blocks that the adversary has not published yet in the same interval. So for example, imagine the honest miner creates block 1. Then the adversary has no hidden blocks from 0 to 1. That means that block 1 satisfies our definition, and block 1 is our next checkpoint. But imagine now that the adversary creates block 2, but the adversary doesn't publish block 2. Now, once the honest miner creates block 3, and block 3 is not a checkpoint because the adversary has one hidden block from 1 to 3. Therefore, 3 is not a checkpoint. For the same reason, 4 is not a checkpoint. But now when the adversary publishes block 5 and 7 and forks block 6, from the path from 1 to 5, the adversary has one block in the longest path, and he also has one hidden block. And this satisfies our definition. That means that block 5 is our next checkpoint. What is nice about this structure is that we can prove a reduction where for any strategy, we can show that that strategy can be transformed in a strategy that would never remove a checkpoint from the longest path. That means that there is an optimal strategy that whenever a new checkpoint is defined, our strategy resets the state of the optimization that the adversary is doing. And whenever a checkpoint is defined, the adversary forgets everything that happened so far, and he just starts optimizing his strategy from the beginning. In addition, prove that the expected time it takes to define a new checkpoint is finite. So that means that this optimal strategy for the adversary can be represented by a positive recurrent Markov chain, which is the main ingredient to give a very strong characterization of the adversary optimal strategies, that this strategy is provably positive recurrent. So this allows us to conclude that for the first case, because block 1, if block 1 was created by the honest miner, block 1 becomes a checkpoint, then the adversary would never forks block 1. But imagine if the adversary instead had created block 1, if the adversary published block 1 would also satisfy our definition of checkpoint. So in both cases, the game would return to the initial state whenever a block is created. That's just equivalent to say that the optimal strategy for the adversary would be the honest strategy. So we just need to consider the case where the adversary creates block 1, but he doesn't publish it. So for the first case, imagine the adversary creates the first block, but the honest miner creates the second one. For this particular case, we observe that we have a tie between the adversary and the honest miner. And we can prove that the probability that the adversary would ever be able to publish block 1 is at most alpha over 1 minus alpha. The high level of the proof is to couple this game with a Markov chain. So imagine we had a Markov chain over the integers is starting at state 1. And our Markov chain increments the state whenever the honest miner creates a block with probability 1 minus alpha. And recall 1 minus alpha is strictly bigger than half. And our Markov chain decrements the state whenever the adversary creates a block. So the adversary can only publish block 1 if this Markov chain returns to reach the state 0, which is which the probability is exactly alpha over 1 minus alpha. So no matter what the adversary do, the probability that he could ever publish block 1 if he reaches this particular state is bounded by alpha over 1 minus alpha. So this gives a limitation of how much the adversary could extract a payoff from the second case. For the third case, we basically proved that the optimal strategy when alpha is sufficiently small is identical to what the selfish mining strategy would do. And the reason is that if the adversary creates, when the advantage of the adversary reduced to a single block, then the adversary could either choose to publish block 1 and 2 or not. But if he doesn't publish block 1 and 2, then he risks losing his advantage. And for the same reason that we had in the second case, the probability that the adversary wins a tie-break is at most alpha over 1 minus alpha. So this allows us to bound how much the adversary could extract from any reachable state in this particular optimization. And that what gives us our strong characterization of the optimal strategy for the adversary. So to summarize, our main result is that honest mining becomes a Nash equilibrium if all miners own at most 30.8% of the coins. Our second result is that honest mining we actually give a explicitly strategy that is better than honest mining if this miner owns more than 32.8% of the coins. So we give a threshold where honest mining is optimal. Interestingly, we know from the prior work on proof of work that Serpstein, Sompolonsky, and Zohar, they explicitly computed the threshold where proof of work is optimal, where proof of work is a Nash equilibrium. And so our results strictly show that proof of stake is actually the threshold where proof of stake is a Nash equilibrium strictly smaller than in proof of work. But we obtain a bound that is very close to what is known for proof of work, which means that proof of stake can approximate the guarantees that we have in proof of work. So to conclude, proof of stake with trusted randomness allow us to overcome the limitations that we have in proof of work and can approximate the security guarantees that we have. One very interesting direction is how we can actually leverage the theory that we build here and is use existing public random sources to design proof of stake blockchains that obtain the strong properties that we provide in this work. Thank you very much.